Ever wondered why some solids melt into liquids with just a touch of warmth, while others demand, the intense heat of a furnace?
Yeah, it's quite a range, isn't it?
Or how a chemist can confidently declare a compound pure or maybe identify it just by watching a tiny sample transform from solid to liquid.
It's truly all about the hidden dance of molecules. Today, we're embarking on a deep dive into one of organic chemistry's most fundamental and really practical properties,
Hmm.
the melting point.
Okay.
We'll peel back the layers to understand the invisible forces that dictate when a solid, well, gracefully transitions into a liquid.
Right.
We'll explore how this seemingly simple measurement acts as a kind of molecular fingerprint for both identification and purity. And then, crucially, we'll walk through the actual lab procedure, from preparing your sample to interpreting your results.
Think of this as your essential guide, maybe a shortcut to truly understanding a core concept you'll use constantly in the lab. We'll be pulling insights from the sources, so get ready for some genuine aha moments about why even a tiny impurity can dramatically shift an entire experiment.
Mm-hmm.
For you specifically, we're going to really hone in on the melting point lab procedure itself. Not just the theory, but the actual steps you'll take, how to collect the data, and what results you should expect, and the conclusions you can confidently draw.
Yeah, that's cute.
Plus, we'll connect it all to the essential glassware you'd be using along the way.
Indeed, knowing these principles helps you move beyond just doing an experiment. It really empowers you to truly understand what's unfolding at the molecular level.
Yeah.
And crucially, why it matters in practical terms, like getting an accurate melting point determination.
Okay, let's unpack this. Before we even talk about how to measure a melting point, we kind of need to grasp the foundational why. Why do substances melt at specific temperatures? And it all boils down to these things called intermolecular forces, right? These attractions between molecules.
Precisely. They're distinct from the much stronger covalent bonds within them. That's a really important point.
Okay.
You can imagine molecules as, I don't know, tiny magnets or maybe sticky little balls. The intrinsic strength of that stickiness, the attractive forces between them, dictates how much energy, specifically in the form of heat, is required to loosen those attractions.
To let them move freely.
Exactly, to allow the molecules to finally move freely as a liquid. These are our intermolecular forces, or IMFs, and it's a crucial distinction that they are considerably weaker than the actual covalent bonds within a molecule.
So we're not breaking the molecules themselves apart when something melts.
No, not at all. For a solid to melt, we're merely overcoming these weaker external attractions.
So let's start with the weakest, but the ones that are always there.
Right.
London dispersion forces, or LDFs. I remember these are present in all molecules, polar or nonpolar.
That's right. They're universal.
What's the core idea behind them, these fleeting attractors, as they're sometimes called?
Well, the core idea is that LDS result from the attraction of correlated temporary dipoles.
Okay, temporary dipoles. That sounds a bit abstract.
It does, yeah. Let's break it down. Even in a perfectly nonpolar molecule, electrons are in constant motion, like a swarming cloud.
Right.
At any given instant, there might be a fleeting, uneven distribution of that electron density. One side of the molecule might momentarily become slightly more negative and the other slightly more positive.
Just for a split second.
Exactly. That brief imbalance creates a transient or temporary dipole. What's truly fascinating here is how these temporary dipoles don't act in isolation.
Okay.
When one molecule develops such a temporary dipole, it can actually induce a similar synchronized temporary dipole in an adjacent molecule.
Oh, so it's like a domino effect almost.
Yeah, exactly. It's like a chain reaction of electron cloud distortions, leading to a very weak but undeniably real attraction between them.
So it's not a permanent charge, but a constantly shifting, induced attraction that somehow coordinates between molecules. That's subtle but makes sense. How does that translate into the kinds of compounds where LDFs are like the main force holding them together?
You hit on a crucial point. These forces are universal, present in every molecule, and their collective strength, dictated primarily by molecular size and shape, is often the foundational reason why substances like, say, long-chain polymers or even noble gases can exist as liquids or solids at all.
Ah.
The real insight is that larger molecules with more electrons have more opportunities for these temporary dipoles to form, leading to stronger LDFs overall.
Can we see that with an example?
Yeah, absolutely. Let's illustrate this with some simple alkanes, all with the molecular formula C5H12, but very different structures. Consider N-pentane. It's a linear chain, and it has a boiling point of 36 degrees C.
Okay.
Then there's isopentane, which is a branched isomer. Its boiling point is lower, 28 degrees C. And finally, neopentane, which is even more branched and takes on a very sort of spherical shape, has a boiling point of just 10 degrees C.
Wow, that's a pretty significant difference in boiling points for molecules that are essentially made of the same atoms. How does their shape cause such a dramatic effect on these fleeting attractions?
Well, if we connect them to the bigger picture, a larger, more linear surface area, like you find in N-pentane, allows for more extensive and effective points of contact between neighboring molecules.
More places to stick together.
Exactly. This means there are more opportunities for those correlated temporary dipoles to form and interact across a greater area. That leads to stronger overall London dispersion forces.
Okay.
Conversely, the more branched and spherical a molecule, like neopentane, the smaller its effective surface area for contact between molecules. Imagine trying to get two, fuzzy tennis balls to stick together versus two long, furry pipe cleaners.
The pipe cleaners have way more contact points.
Precisely. Less surface contact means fewer, weaker LDFs, requiring less energy to overcome them. This leads to a lower boiling point, and by extension, a lower melting point, as the same forces dictate both. It's all about how efficiently they can stick to each other due to these transient electrical attractions.
Okay, that makes perfect sense for those fleeting LDFs. So what's the next step up in terms of molecular stickiness? This is where polarity comes in, right?
That's a great question. The next step up are dipole attractions. These occur in molecules with permanent dipole moments.
Permanent, okay. So unlike the LDS.
Right. Unlike the fleeting instantaneous dipoles of LDFs, a permanent dipole moment arises from fundamental and consistent differences in electronegativity between atoms within a molecule.
Electronegativity. The atom's ability to pull electrons towards itself in a bond.
Exactly. When atoms with different electronegativities form a covalent bond, the electrons are unequally shared, pulled closer to the more electronegative atom. This creates enduring partial positive and negative charges, what we call bond dipoles. Now, if the molecule's overall geometry, its 3D shape, is such that these bond dipoles don't symmetrically cancel each other out.
Geometry matters again.
Critically, if they don't cancel, the molecule as a whole will possess a permanent dipole moment. These constant partial charges then create constant rather than temporary attractions between neighboring molecules. This permanent pole requires, significantly more energy to overcome than just London dispersion forces.
So it's not just about having polar bonds within a molecule, but also about the overall 3D shape of the molecule, influencing whether those polarities add up or cancel out.
You've got it. That's a critical distinction. Take formaldehyde, CH2O, for example. It has a molecular dipole moment of 2.3 darbies, making it quite polar.
Okay.
Its central carbon is double bonded to oxygen, which strongly pulls electron density, and the molecule is planar. This arrangement ensures that the polarity isn't canceled.
Right.
Now compare that to carbon dioxide, CO2. It has two very polar carbon-oxygen double bonds, but it has a zero net dipole moment.
Why is that? Because it's linear.
Exactly. Because the molecule is linear, the two bond dipoles pull in perfectly opposite directions, precisely canceling each other out. This geometric cancellation means that in terms of dipole interactions, CO2 acts like a nonpolar molecule, even though its bonds are polar.
Okay, so shape is key. Building on that point, what about cis and trans isomers? These are molecules with the exact same atoms, same connections, but different arrangements in space. Does that affect their dipole attractions?
My intuition tells me yes, because their shapes are different, which would inherently affect how the dipoles align and interact.
Right. It feels like it should matter.
Your intuition is spot on. Consider cis-sp2 versus trans-sp2-Ne. In cis-sp2-Ne, both methyl groups are on the same side of the double bond. This asymmetry leads to a small but significant net dipole moment, making the molecule polar. In contrast, trans-sp2-Ne, with its methyl groups on opposite sides, is essentially nonpolar because its individual bond dipoles cancel out due to its symmetrical arrangement.
So the cis one has stronger dipole forces.
Correct. This difference means cis-sp2 typically has a slightly higher boiling point and generally a different melting point too.
And does this effect get bigger if the polar bonds are, more polar?
Oh, definitely. The effect of bond polarity in molecular geometry is even more strikingly apparent in the Twom-Gilder-2 dichlorothenes. They have strongly polar carbon-chlorine bonds.
Okay.
The cis isomer possesses a substantial dipole moment of 2.4 D, which translates to a boiling point 12 degrees higher than that of the trans isomer, which has a zero dipole moment due to its perfect symmetry.
12 degrees. That's quite a jump just based on geometry.
It vividly demonstrates how molecular geometry profoundly influences the presence and magnitude of molecular dipole moments and consequently impact physical properties like boiling and melting points. These permanent dipoles require notably more energy to overcome than the fleeting London dispersion forces alone.
Okay, now for what feels like the heavy hitter of intermolecular forces, hydrogen bonding. This one always strikes me as particularly strong and really significant.
It absolutely is. Though it's important to clarify, a hydrogen bond is not a true covalent bond, but rather a particularly strong dipole attraction.
Ah, okay, so a special kind of dipole.
Exactly. It forms when a hydrogen atom is covalently bonded to a highly electronegative atom, specifically oxygen, nitrogen, or fluorine. In the realm of organic chemistry, this primarily means OH and NH bonds. HF bonds aren't that common in organic molecules.
Got it. OH and NH.
The reason for its exceptional strength lies in the strong polarization of these OH and NH bonds. Oxygen and nitrogen are highly electronegative, aggressively pulling electron density away from the hydrogen atom.
Leaving the hydrogen kind of naked, electronically speaking.
Pretty much. It leaves the hydrogen atom with a substantial partial positive charge, rendering it quite electron-seeking or electrophilic in chemical terms. This means it has a strong affinity for the non-bonding electrons, the lone pairs, on an oxygen or nitrogen atom of a neighboring molecule.
So it's like a tiny superpolarized hydrogen acting as a mini magnet for lone pairs on other nearby molecules.
That's a great way to put it, yes.
So it's essentially this deeply exposed positive hydrogen attracting the electron-rich areas on other molecules. And while we say it's strong, it's still not a true bond in the covalent sense, right? What's the energy difference we're talking about, like compared to a real bond?
That's a crucial point to remember for context. While hydrogen bonds are indeed potent for an intermolecular force, their energy is still an order of magnitude weaker than true covalent bonds.
Okay.
Breaking a hydrogen bond requires about 20 kilomole, or roughly 5 kilomole. That's a stark contrast to the approximately 400 kilomole, or about 100 kilopalm, needed to break a covalent bond like a CH, NH, or OH within a molecule.
Wow, okay. So a big difference. Still strong enough to matter a lot for melting and boiling, though.
Oh, absolutely. Hydrogen bonds are definitely strong enough to significantly influence physical properties, but they are still not on the same level as the forces holding atoms together inside a molecule.
Here's where it gets really interesting. How does that energy difference translate into real-world effects, like the vastly different boiling points we sometimes see between isomers?
Right. Let's consider a classic pair. Ethanol and dimethyl ether. Both share the same molecular formula, C2H6O, making them isomers.
Same atoms, different arrangement.
Exactly. Ethanol possesses an OH group, which allows it to form extensive networks of hydrogen bonds with other ethanol molecules. Dimethyl ether, however, despite having an oxygen atom, lacks a hydrogen directly bonded to that oxygen. It just has CH and CO bonds, so it cannot hydrogen bond with itself.
And the consequence?
Ethanol boasts a boiling point more than 100 degrees C higher than that of dimethyl ether.
100 degrees, just from that OH group.
Yes. This dramatic difference is almost entirely attributable to the powerful influence of hydrogen bonding in ethanol, which demands significantly more energy to separate the molecules into the gas phase.
Does it work the same way with NH bonds? Like, more NH bonds mean stronger forces.
We observe a similar phenomenon with the isomers of C3H9N. Trimethylamine, for instance, has no NH hydrogens, so it can't hydrogen bond with itself. Ethylmethylamine has one NH bond, so it can participate in hydrogen bonding to a greater extent, and its boiling point is considerably higher than trimethylamine's.
Right.
And then propylamine, with two NH hydrogens, can form even more extensive hydrogen bond networks, and consequently exhibits the highest boiling point of the three.
So there's a clear trend.
The general principle holds. The more opportunities for hydrogen bonding a molecule has, the stronger its collective intermolecular forces, and thus the greater the energy required to overcome those forces, leading to higher melting and boiling points.
So what does this all mean for us in the lab? And all these forces, from the fleeting London dispersion forces to the permanent dipole attractions, especially the incredibly influential hydrogen bonds, they ultimately dictate how tightly molecules hold on to each other in a solid state. And that's exactly why melting point becomes such a crucial piece of information for a chemist, isn't it? Especially when you're trying to characterize a compound or check its purity after a reaction.
Precisely. Because these forces are so intricately specific to a molecule's unique structure and the way it can interact with its neighbors, the melting point provides an incredibly reliable and informative indicator for chemists. It's not just a number, it's like a little window into the molecular world.
So if these intermolecular forces are so specific to a molecule's structure and its arrangement, does that essentially mean its melting point is like its unique ID, its molecular fingerprint?
Absolutely. The melting point of a pure substance is one of its fundamental physical constants, akin to a characteristic fingerprint.
Yep.
For a pure crystalline organic compound, it will typically melt over a very narrow and specific temperature range, often just 1 to 2 degrees Celsius. This sharp melting behavior is the hallmark of both purity and identity.
That's brilliant. So if I'm in the lab and I've synthesized a new compound or isolated something, how do I actually use that melting point as an identifier? Say I get a sharp melt at 120, 121C.
It serves as a quick yet powerful preliminary identification tool. Let's say you've synthesized an unknown compound, meticulously purified it, and then measure its melting point, finding it melts sharply at exactly 120, 121 degrees C.
Okay.
You can then compare this value to a comprehensive database or literature values of known compounds. If a known compound, let's call it compound X, is documented to melt at 120, 121 degrees C, this observation provides a strong preliminary indication that your unknown might indeed be compound X.
So it narrows things down.
Significantly.
Right.
While it's not definitive on its own, you'd often need further tests like spectroscopy, IR, NMR, etc. It significantly narrows down the possibilities and guides your next steps in characterization. This concept subtly connects to broader ideas in physical chemistry, too, like how molecular weights can be determined by methods that relate the freezing point depression or boiling point elevation of a solvent to the mole concentration of the unknown.
Colligative properties.
Exactly. What this implicitly tells us is that freezing point, and thus melting point for a pure substance, is a fundamental, measurable characteristic intrinsically linked to the compound's identity and its concentration within any mixture.
That's incredibly useful for identification. But you also mentioned purity. How does melting point help us assess how pure our sample is? Because in organic chemistry, achieving a pure product often feels like, well, the main goal after a complex synthesis.
It's one of the most critical and frequently used applications in the lab, especially for you as an organic chemistry student. As we discussed, a pure sample will exhibit a sharp, narrow melting point range.
That 1-2 degree window.
Right. The presence of even small amounts of impurities, however, will almost invariably have two distinct effects. First, it will typically depress the melting point.
Meaning it starts melting lower.
Exactly. It'll begin to melt at a lower temperature than the pure substance. Second, and equally important, it will significantly broaden the melting range. Instead of melting over a tight 1 to 2 degrees, you might observe it melting over 5, 10, or even more degrees Celsius.
Wow.
This phenomenon is a direct consequence of freezing point depression, a concept you might recall from general chemistry.
So essentially, the impurity acts like a disruptive element. It makes it easier for the solid crystal lattice to kind of fall apart and transition to a liquid.
Precisely. Imagine trying to stack perfect, identical Lego bricks into a solid, highly ordered structure. That stack is uniform, strong, and melts, or, disassembles predictably.
Okay.
Now imagine attempting to build that same structure using a random mix of Legos and Duplos.
It'd be a mess, weaker, less stable.
Right. The mixed stack is weaker, less structured, and requires considerably less effort to destabilize. Similarly, impurities disrupt the highly ordered symmetrical crystal lattice of the pure compound. This makes it easier for the solid to transition to a liquid at a lower temperature.
And the broadening, why does the range get wider?
The broadening of the range occurs because as the solid starts to melt, the concentration of the impurity in the remaining solid continuously changes. This leads to a progressive depression of the melting point over a wider temperature span, creating that drawn-out melting profile.
See.
So a broad and depressed melting point range is a clear and unmistakable signal that your sample isn't as pure as you'd ideally like.
That's a super clear analogy. So melting point can tell us what we have, potentially, and how pure it is. But what about really subtle differences, like between isomers? Same molecular formula, but different arrangements of atoms. Can it distinguish between those?
This raises another important question that chemists frequently encounter. If you had different isomers, particularly stereoisomers, could melting points still serve as a diagnostic tool?
Yeah, can it tell them apart?
The answer is a resounding yes. Different isomers, even those with the same molecular formula and connectivity, often possess distinctly different physical properties, including unique melting points.
Why is that?
It's because their overall molecular shapes, and critically, how these molecules are able to pack together into a solid crystal lattice, are different. These subtle differences in crystal packing lead to different intermolecular forces being established between the molecules.
Which means different amounts of energy needed to melt them.
Exactly, different energy requirements, which in turn manifest as unique melting points.
Can you give us an example where this plays out, perhaps with some trickier isomeric forms?
Certainly. Let's consider cis-1-baryl-2 dichlorocyclopentane and its trans enantiomers.
Oh, he says trans on a ring and enantiomers. Remind me quickly.
Sure, enantiomers are non-superimposable mirror images like your left and right hands. And interestingly, the cis form here, where both chlorines are on the same side of the ring, is what we call an achiral meso compound.
Meso, meaning it has chiral centers but is overall not chiral because of symmetry.
Precisely. It has an internal plane of symmetry that makes the molecule superimposable on its mirror image, so it's achiral. Its trans counterparts, however, where the chlorines are on opposite sides, exist as a pair of these mirror image enantiomers. They are chiral.
Got it. So 3 distinct species here. The cis, meso, and the 2 trans enantiomers.
Correct. Now, these 3 compounds have the exact same atoms and the same sequence of bonds, but their spatial arrangements are distinct. Because of these distinct spatial arrangements, their molecules will pack into crystal lattices in different ways.
Different packing, different forces.
Different melting points.
Yeah.
The collective intermolecular forces within these distinct crystal structures, and therefore the energy required to break them down, will be different.
So the cis form would have one melting point.
And the trans enantiomers would have a different melting point. Now, the 2 trans enantiomers themselves, being mirror images, would have the same melting point as each other, but that value would be different from the cis form.
That's cool.
It beautifully demonstrates the power of melting point as a diagnostic tool for even very subtle structural differences. It highlights its utility in distinguishing between various isomeric forms during synthesis and characterization in the lab.
So we've thoroughly covered why melting points are important and what they tell us about a compound's identity and purity. But to actually harness this information, to get that truly reliable molecular fingerprint, you first need a pure sample, obviously, and then you need to perform the measurement correctly.
Absolutely. The technique matters hugely.
Let's walk through the essential steps you take in an organic chemistry lab. Almost like a guided tour of the actual melting point lab procedure, focusing on precision and getting good data.
Yeah, let's do it. Performing a melting point determination is one of the first and most fundamental techniques you'll master in organic chem lab. It's deceptively simple in concept, but it really requires precision, keen observation, and an understanding of potential pitfalls.
Okay.
Let's break down the procedure, from preparing your sample right through to interpreting your results and the conclusions you can draw.
First things first, preparing the sample. It's not just scooping it out of a beaker and tossing it into the apparatus, is it? I assume not.
Not at all. Proper sample preparation is absolutely critical for obtaining accurate and meaningful results. You need a sample that is both completely dry and finely powdered.
Why dry?
Well, if your sample isn't perfectly dry, any residual solvent will act as an impurity. And as we just discussed, what do impurities do?
They depress and broaden the melting point.
Exactly, so you'll get a wrong reading. Furthermore, grinding it into a fine powder ensures uniform heat transfer and allows for tight, even packing in the capillary tube.
So if I've just recrystallized a compound, which is a super common purification step, how do I ensure it's properly dry and finely powdered for this next step?
Good question. After you've performed a vacuum filtration to collect your crystals, maybe using a Buchner funnel and a suction flask, which we'll talk about soon, you'd typically let them air dry thoroughly.
You just leave them out.
You could leave them on a watch glass exposed to the air, maybe covered loosely with another watch glass or filter paper, or ideally put them in a desiccator to remove any last traces of moisture.
Okay, desiccator's better.
Generally, yes. Once visually dry, use a clean, dry spatula or maybe a mortar and pestle to gently crush any larger crystals until you have a fine, uniform powder. This fine powder maximizes the surface area, ensuring efficient and even heat transfer during the melting process itself.
Then comes loading the capillary tube itself, those tiny, delicate glass tubes. How much sample do we need and how do we get it in there correctly? It's tricky.
It can be a little fiddly at first. You'll take a melting point capillary tube. It's a very thin glass tube, sealed at one end. Tap the open end gently into your finely powdered sample so that a small amount enters the tube.
Just dip it in.
Yeah, just gently tap it in. Then you need to get that sample to the very bottom into the sealed end. There are a few tried and true tricks.
Like what?
You can gently tap the sealed end of the tube on the bench top. Or a common method is to drop the capillary tube, sealed end down, through a longer hollow glass tube onto the bench. Gravity and the impact settle the solid down.
Ah, clever.
Some labs even have small electric vibrators designed for this. You're aiming for about 2-3 millimeters of tightly packed solid at the bottom of the tube. Not too much.
Why is it so important for it to be tightly packed? And why such a small amount, only 2-3 millimeters?
Tightly packed sample ensures excellent thermal contact between the solid particles and the glass, and it prevents air pockets. Air pockets would lead to uneven heating and an inaccurate melting range.
Makes sense.
And the small amount. As for the small amount, it's crucial because it allows for rapid and uniform heat transfer throughout the entire sample. If you use too much sample, you'll observe a broad, drawn-out melt, simply because the heat cannot penetrate evenly through a larger volume of solid in a short amount of time. This leads to an artificially wide range, even if your sample is pure.
Okay, with our perfectly prepared and loaded capillary, now for the actual measurement. Most organic chemistry labs use a specialized melting point apparatus for this, right? Not just like a beaker and a thermometer over a Bunsen burner.
Oh, definitely not. Modern organic chemistry labs rely on sterilized melting point apparatus, things like a Meltemp or similar electrothermal devices. These units provide precise and controlled heating, which is fundamental for accurate determinations.
Okay.
You'll insert your loaded capillary tube into one of the designated slots. Most apparatus allow for 2 or 3 capillaries simultaneously.
Oh, that's handy. Why would you run more than one?
It's incredibly useful for running duplicates to check consistency, or for performing a mixed melting point experiment, which we should definitely talk about.
Okay.
Many units also feature a magnifying lens and internal illumination to help you clearly observe the tiny sample as it melts.
And temperature control is obviously key here.
Yeah.
What's the standard approach? You don't just crank it up, right?
Temperature control is paramount. You'll typically have controls for the heating rate. The initial heating can be relatively rapid, maybe 5-10 degrees Celsius per minute, just to quickly bring the temperature up to within, say, 10-20 degrees below the expected melting point.
So you need a rough idea first.
Yeah, maybe from a quick preliminary run or literature data. But once you enter that critical window, that 10-20 degree range below the expected melt, you must slow down the heating rate.
How slow?
Very controlled. Aim for 1-2 degrees Celsius per minute. This slow, steady rate is absolutely paramount for an accurate determination of the melting range.
Why is it so crucial to slow down the heating rate at that point? What happens if I rush it? If I'm impatient?
If you heat too quickly, there's a significant lag between the temperature of the heating block or oil bath inside the apparatus and the actual temperature of your tiny sample and the thermometer itself. They just can't keep up.
So the thermometer reading is wrong.
Exactly. The thermometer won't accurately reflect the sample's true temperature at the moment it starts melting. A rapid rise will invariably give you an artificially high and broad observed melting point. Why? Because the heating element is getting hotter faster than the sample and thermometer can equilibrate. The sample begins to melt before the thermometer has accurately registered its true temperature.
Ah, okay. So rushing gives you bad data.
It results in inaccurate data and potentially flawed conclusions about purity and identity. Patience is key here.
So with the apparatus heating slowly, I'm peering through the magnifier. What exactly am I looking for as the sample warms up? What defines the start and end?
You're carefully observing and looking for 2 key temperatures that define the melting range. The first is the temperature at which you observe the first clear sign of liquefaction.
What does that look like?
This isn't just your sample sweating or shrinking or maybe changing transparency slightly. Those can happen before melting. It's when the very first definite drop of liquid appears, usually at the edges of the sample or where the solid meets the glass. You need to record that temperature immediately.
That's T1, the lower limit.
Correct. That's the lower limit of your melting range.
And the second point, when the entire sample is liquid, that's T2.
Exactly. The second temperature you record, T2, is when the entire sample has completely turned to a clear liquid. There should be no visible solid particles remaining, no murky solid clumps floating around. Record that temperature.
Got it.
The difference between these 2 observed points, the first sign of liquid, T1, and the complete liquefaction, T2, is your observed melting range. For instance, if you note the first liquid at 120 degrees C and it's entirely liquid at 121 degrees C, your recorded melting point is 121 degrees C.
So I've got my observed melting range, say 120, 121 degrees C. What does that tell me? How do I interpret these results?
A sharp melting range, typically 1 to 2 degrees Celsius like that, is a very strong indication of a pure compound.
Good news then.
Very good news. It tells you your substance is likely what it should be and has high purity. If you've synthesized a known compound and obtained this kind of sharp range that matches the literature value, you can be confident you've succeeded in both the synthesis and the purification steps. This is the result you always strive for.
But what if it's not a sharp range? What if I observe something like, I don't know, 115, 120 degrees C, and the literature says the pure stuff should be 120, 121 degrees C?
Okay. A broad and depressed melting range, meaning it starts lower than the literature value, 115 versus 120, and melts over several degrees, a 5-degree range here, is a definitive sign of impurities.
Right. We talk about that depression and broadening.
Exactly. The broader the range and the lower the overall temperature compared to the pure compound's known melting point, the more impure your sample is likely to be. This is where you, as a discerning chemist, would draw the conclusion, okay, this sample is not pure enough, it's time for another recrystallization.
Or some other purification.
Or I need to perform another purification step, perhaps chromatography, to isolate the pure product. It's an invaluable quality control check, telling you if you need to clean things up more.
That makes total sense. So it helps confirm purity.
Yeah.
But for confirming identity, beyond just matching a number from the book, you mentioned a really clever technique called a mixed melting point. How does that work in practice?
Yes. The mixed melting point is a brilliant and often definitive technique for confirming the identity of an unknown solid, especially if another known compound has a very similar melting point.
Okay, how to set it up?
Let's say you have your unknown sample that you've isolated, and it melts sharply at, say, 121 degrees C. You suspect, based on its melting point and perhaps other preliminary tests like how it was made, that it might be compound X, which is known from literature to also melt at 121 degrees C.
Right, they match.
To definitively confirm if your unknown is compound X, you would first obtain a small, pure known sample of compound X from a reliable source. Then, you carefully mix a small, roughly equal amount of your unknown with this known, pure sample of compound X. You need to grind them together thoroughly, maybe with a spatula on a watch glass or in a small mortar and pestle, to ensure they're intimately mixed, totally homogeneous.
So a 50-50 mix, ground up well.
Exactly. Finally, you take the melting point of this meticulously prepared mixture, using the same careful technique we just discussed, slow heating rate near the melt, observe T1 and T2.
And what should I expect to see if my unknown truly is compound X? If I guessed right.
If your unknown is compound X, then when mixed with pure compound X, the mixture will behave just like the pure compounds. It will melt sharply at the exact same temperature range, 120 to 121 degrees C.
No depression, no broadening.
None at all. This happens because adding a pure compound to itself doesn't introduce an impurity, it just makes the sample larger. So a sharp, undepressed melting point for the mixture is definitive proof that your unknown is indeed compound X.
But what if I'm wrong? What if my unknown isn't compound X, even if they happen to have similar individual melting points?
This is where the magic happens. If your unknown is not compound X, even if it individually melts at a very similar temperature, say 120, 121 degrees C, the mixture you prepared will show a significantly depressed and broadened melting range.
Why?
Because in that scenario, your unknown is acting as an impurity to the known compound X, and compound X is acting as an impurity to your unknown. They are different substances.
Each contaminates the other.
Precisely. And as we've established, any impurity will depress and broaden the melting point. So observing a depressed and broadened melting range for the mixture, maybe it melts from 110 on 18 degrees C instead of 120, 121 degrees C, is conclusive proof that your unknown is not compound X.
That's really clever.
It's a highly definitive test for identity, providing a clear yes or no answer, especially useful when you're trying to distinguish between compounds with very close melting points. It's a classic organic chemistry technique.
So we've walked through the why, the what, and the how of melting points. But to actually do any of this, to synthesize a compound in the first place, purify it, to get that pristine sample, and then perform this crucial melting point determination, you need the right tools.
Absolutely. Technique is nothing without the proper equipment.
Let's take a virtual tour of some of the essential glassware and equipment you'd encounter in an organic chemistry lab.
Yep.
Let's focus on those critical equipments for preparing, purifying, and ultimately characterizing your compound through its melting point. It's like a chef reviewing their specialized kitchen equipment, right? Each piece playing a vital role.
Indeed, the right equipment is absolutely crucial for safety, efficiency, and obtaining accurate results in organic chemistry. This field relies heavily on specialized glassware designed to contain reactions, facilitate separations, and purify products. Using the correct piece of equipment for each step of a procedure isn't just good practice, it's fundamental to success. We can touch on some general lab essentials first, then move to more organic chemistry-specific items, maybe contextualizing their use within the workflow of preparing a sample for melting point analysis.
Sounds good. What are some of the absolute basics we see everywhere?
Okay, let's start with some general lab workhorses that are indispensable. The Erlenmeyer flask, everyone knows this one. It's your basic workhorse for mixing and holding liquids. Its conical shape is particularly useful for titrations, as it minimizes splashes, and it's excellent for recrystallizations where you might need to swirl a hot solution vigorously without losing product.
Right, you use those all the time.
Then there's the simple glass funnel. Also indispensable for transferring liquids without spillage or for simple gravity filtrations when you're trying to separate a solid from a liquid using filter paper, maybe to remove some unwanted solid crud before crystallization.
And what about the smaller yet mighty tools that are always on hand? Things you use to handle the chemicals.
Absolutely. The spatula is the humble but mighty tool for scooping and transferring solid chemicals. You'll use it constantly for weighing things out, for adding reagents, for preparing your sample for the capillary tube, or for transferring your recrystallized product off the filter paper.
Can't live without a good spatula.
Nope. The wire gauze, often with a ceramic center, provides a stable, even surface when heating beakers or flasks with a Bunsen burner, diffusing the heat to prevent cracking and allowing for controlled heating. Though direct heating with burners is less common now with safer options.
True. What about covering things or weighing?
A watch glass is surprisingly versatile. Useful for covering beakers to prevent evaporation or contamination, for evaporating small amounts of solvent, maybe dry a sample, or, very critically, for weighing solids accurately on a balance. You put the watch glass on the balance, tare it, add your solid. And for approximate measurements of liquid volumes, you'll reach for a graduated cylinder. It's not for high precision like a pipette, but it's good for quick, decent estimates of volume when preparing solvents for recrystallization, for example.
Okay.
Finally, crucible tongs are vital for safely handling hot crucibles, or sometimes even hot beakers or flasks, keeping your hands away from heat when retrieving dried samples from an oven, for instance. Safety first.
That covers the general basics pretty well. Now let's get into the more specialized equipment, the stuff that really makes you think organic chemistry lab. These are the tools that enable the complex purifications that lead to that pure sampling we need for an accurate melting point.
Precisely. These pieces are often ingeniously designed for the specific needs of organic reactions and purifications. First, consider the stemless funnel. This is a specialized piece, really excellent for hot gravity filtrations, especially during recrystallization.
Why stemless?
Its crucial design feature, the lack of a long stem, prevents premature crystallization of your desired compound within the stem as the hot, saturated solution cools while passing through. This can be a real headache when you're trying to recover your pure product. It gets stuck. The stemless design minimizes that cooling surface.
Okay, that's smart. What about heating things safely?
Right. The hot plate is ubiquitous for controlled heating of solutions and reactions, often equipped with magnetic stirring capabilities to ensure even mixing and temperature distribution. Very common.
Yeah, see those everywhere.
But when you need more serious, consistent heating, particularly with round bottom flasks, you'll reach for a heating mantle. This provides gentle, even heat distribution around the curved surface of a round bottom flask. It's much safer than an open flame from a Bunsen burner, especially when you're working with highly flammable organic solvents, which is most of the time.
Good point. Safety is huge with organic solvent.
Absolutely. Now, when you're ready to collect a solid product, perhaps the crystals you've painstakingly recrystallized to get pure enough for a melting point.
Yeah.
You'll definitely need a suction filter flask, also widely known as a Buchner flask. This is a thick-walled flask specifically designed to withstand the vacuum applied during filtration. It's got that sidearm for the vacuum hose.
Okay.
It's used in conjunction with a Buchner funnel, which is typically a porcelain or plastic funnel with a flat, perforated plate. You put filter paper on the plate.
Right, I've seen those setups.
Together, with filter paper sized correctly and a good seal, they enable rapid vacuum filtration. It efficiently pulls the solvent away, separating your solid product much faster than gravity filtration, a crucial step before drying your sample for melting point analysis.
The round bottom flask is a classic, isn't it?
Yeah.
It just screams organic chemistry. What's its special appeal and how does it connect to preparing our melting point sample?
The round bottom flask is truly the quintessential reaction vessel in organic chemistry. Its spherical shape allows for incredibly even heating and efficient stirring, which is crucial for maintaining consistent reaction conditions during synthesis. It prevents bumping, too.
Oh.
It comes in various neck configurations, single neck, 2 necks, 3 necks, allowing for the attachment of other apparatus, creating complex setups for distillation, reflux, or additions. Any compound you synthesize and then want to measure the melting point of would likely begin its life in a round bottom flask.
And speaking of attachments, you need ways to connect things, right?
Exactly. Ground glass joints are standard. A three-way adapter, sometimes called a distilling head, is commonly used in distillation setups. It connects your reaction flask, containing the mixture you want to purify, to a thermometer, to monitor vapor temperature, and a condenser to cool the vapor back to liquid. This is how you might purify a liquid product or solvent.
Right.
Then there's the vacuum adapter. This connects the receiving flask, where your purified liquid collects, to the condenser, and also provides a connection point for the vacuum source in a vacuum distillation setup.
Why vacuum distillation?
It allows you to distill compounds at lower temperatures than their normal boiling points, which is really useful for purifying compounds that might decompose if heated too strongly at atmospheric pressure. Another key purification technique before you get to a solid for melting point.
What about adding multiple things to one flask?
For that, the Claisen adapter is your friend. It's often a Y-shaped or sometimes T-shaped adapter, a real multitasker. It allows 2 different pieces of equipment, like maybe a condenser for reflux and an addition funnel for controlled region addition, to be attached simultaneously to a single neck of a round bottom flask. It really expands the capabilities of your reaction vessel.
Andy.
And a simple but essential piece is the thermometer adapter. It securely holds a thermometer or other probes, like a temperature probe, into a ground glass joint, providing a sealed, precise connection for accurate temperature monitoring during reactions or distillations. Often has a screw cap or fitting to hold the thermometer snugly.
And what about for separating liquids or cooling vapors, which are such common steps in purification leading up to getting that solid?
For cooling hot vapors back into liquid during distillation or reflux, you'll use a distillation column or condenser, often a Liebig, West, or Alling type. It's essential for purification processes like distillation, separating based on boiling points, or reflux, running a reaction at the solvent's boiling point without losing solvent.
Right.
And to separate immiscible liquids, perhaps after an extraction, a very, very common purification technique in organic chemistry, the separatory funnel is your go-to. It's that pear-shaped funnel with a stopcock at the bottom.
Yeah, the sep funnel.
It's uniquely designed for liquid extractions, a technique used to separate compounds based on their differential solubility in 2 immiscible solvents, like water and an organic solvent. This is how you might isolate your desired product from a reaction mixture before you even get to recrystallization or melting point analysis. Finally, holding all this potentially complex glassware together requires support. The ring clamp is a versatile clamp used to secure glassware, like funnels or distillation flasks, to a retort stand or lattice framework, providing essential stability to your entire apparatus and ensuring safe operation. You also use other clamps, like utility clamps.
That's quite the arsenal. It really shows how deliberate and, well, specific organic chemistry operations can be. You're not just mixing things in a general way. You're precisely controlling temperature, carefully separating phases, and meticulously collecting products.
Exactly.
Each piece has a highly specialized purpose, ensuring that complex reactions can proceed safely and effectively, ultimately leading to that pristine sample whose melting point you can accurately determine. It highlights the entire journey from raw materials to a characterized pure compound.
Exactly. Each piece of equipment we've discussed plays a vital role in generating a sample that is pure enough for a meaningful and accurate melting point determination. From synthesis in a round bottom flask to extraction with the separatory funnel, purification by distillation with condensers, to recrystallization aided by Erlenmeyer's and Buchner funnels. Every step contributes to the integrity of that final melting point data. #OuchGabber.
Well, from the invisible forces that govern molecular interactions to the specific glassware that enables complex experiments, and right through the precise steps of the lab procedure itself, we've truly taken a deep dive into the world of melting points and the foundational tools of organic chemistry.
Understanding these core concepts, how molecular structure profoundly influences intermolecular forces, and how those forces elegantly manifest in measurable physical properties like melting point, is truly the bedrock of success and confidence in the lab.
Yeah.
And as we've seen, knowing your tools, and maybe more importantly, knowing why and how to use them in sequence for purification, is half the battle in achieving purity and accurate characterization.
So next time you're in the lab preparing a sample, carefully loading that capillary, or even just, melting an ice cube at home, pause and think about the intricate dance of atoms and the specific energy required to break those attractions. It's all a window into the unique story of each molecule. It's why that careful measurement of a melting point isn't just a number. It's a profound statement about the very essence and identity and purity of your compound.
And maybe consider this. How might a deeper, more refined understanding of these precise molecular forces and their impact on melting points allow us, perhaps in the future, to design materials with exquisitely tailored thermal properties for groundbreaking applications?
Like what?
Imagine tuning the melting point of a drug to control its release profile in the body, or creating a plastic that degrades predictably only when heated to a specific temperature for better environmental control, or maybe developing novel phase change materials for more efficient, sustainable energy storage. The possibilities are truly vast once you master these fundamentals.
Something profound to ponder until our next deep dive. Thanks for joining us.